So in the last class we have seen the definition of Christoffel symbol and some of the properties of the Christoffel symbol. We have also seen that Christoffel symbol of first kind is not a tensor. Now today we will check, so the problem, we'll continue with the problem number 2. Check whether Christoffel symbol of second kind is a tensor or not. Okay, so today we are going to check whether the Christoffel symbol of second kind is a tensor or not. So the definition of Christoffel symbol of second kind is given as Christoffel symbol sigma nu lambda is equal to the fundamental contravariant metric tensor multiplied by Christoffel symbol of first kind. So this is the definition of Christoffel symbol of second kind. I take the transformation. Okay, so prime. I am going to take the transformation from one coordinate system to another coordinate system. So this will be prime. All the quantities I am denoting by prime. Now on the right hand side I can write the transformation for G prime sigma mu. So G prime sigma mu will transform from rho theta, okay, as prime sigma, which is going to rho, and prime mu theta. Okay, this is the transformation for G prime sigma mu. Now for this Christoffel symbol of first kind, in the last class we have seen how it transforms. It do not transform like a tensor. So it has two terms. The first term will be partial derivative of x alpha with respect to x prime mu, x beta with respect to x prime mu, and partial derivative of x gamma with respect to x prime lambda, alpha beta gamma, plus partial derivative of x alpha with respect to x prime mu, second derivative of x beta with respect to x prime mu, x prime lambda, g alpha beta. Okay, so now I have written the transformation. Now I have to open the bracket. So here I have to multiply to first with the first term and with this term. So I'll write partial derivative of x prime sigma with respect to x rho, x prime mu with respect to x theta, x alpha with respect to x prime mu, then x beta with respect to x prime mu, x gamma with respect to x prime lambda, g rho theta, and Christoffel symbol alpha beta gamma, plus now again I have to multiply with the second term. So that will be given by partial derivative of x prime sigma with respect to x rho, partial derivative of x prime mu with respect to x theta, x alpha with respect to x prime mu, x prime mu, x prime lambda, g rho theta, g alpha beta. Okay, so in the first term, if you see here, I have partial derivative of x prime mu in the numerator, and I have partial derivative of x prime mu in the denominator. So these two actually get cancelled, and here if you see these two, right? So the remaining thing is partial derivative of x alpha with respect to x theta, which is Kronecker tensor of alpha theta. Similarly, here also you have Kronecker tensor of alpha theta, which means both of these terms will survive only if alpha is equal to theta, right? Because of the Kronecker tensor. Now I am going to substitute. So this is equal to partial derivative of x prime sigma with respect to x rho, x beta, x prime nu, x gamma, x prime lambda, g rho alpha, alpha beta gamma, plus partial derivative of x prime sigma with respect to x rho, second derivative, then g rho alpha, g alpha beta. Now here you can see that g rho alpha multiplied by g alpha beta. So alpha are summed over, right? So alpha is summed over. So I will get Kronecker tensor of rho beta, because one is the inverse of the other, right? Contravariant metric tensor is the inverse of covariant metric tensor. So if you multiply both, you have to get unity, and unity in tensors is Kronecker tensor. Okay, therefore I can write, and here Kronecker tensor, this term will survive only if rho equal to beta. So I have to substitute rho equal to beta also. So once I substitute rho equal to beta, then I will get partial derivative of x prime sigma with respect to x rho, x beta with respect to x prime nu, x gamma with respect to x prime lambda, Christoffel symbol rho beta gamma, plus partial derivative of x prime sigma with respect to beta, second derivative of x beta with respect to, okay. So the first part transforms like a tensor, right? Here left hand side I have Christoffel symbol prime sigma mu nu lambda. So here I have Christoffel symbol prime sigma mu lambda. Now this is transforming like a tensor, but the second term, okay, the second derivative is present in the second term, and this will make the entire thing not a tensor, not to transform like a tensor. So the second term actually spoils the tensor nature. So due to the presence of second derivative, this term do not transform like a tensor. Therefore, Christoffel symbol of second kind is also not a tensor. So in the last class we have seen Christoffel symbol of first kind is not a tensor. So here we have proved that Christoffel symbol of second kind is also not a tensor. So Christoffel symbol is not a tensor. Okay. It's just a symbol. That's why it's called as Christoffel symbol. It's a symbol. Now, what is the importance of Christoffel symbol? Okay, we have defined it in terms of the metric tensor, fine. But what is the significance of Christoffel symbol? That we are going to see. For that, we should know what is geodesic. So, we learn what is geodesic. And slowly we'll go and see the significance of Christoffel symbol. Geodesic or geodesics. Now, geodesic is a curve joining two points. Okay, if you have 2 points, for example P1 and P2, then geodesic is a curve joining these 2 points in such a way that the distance between these 2 points is always the least. Okay, so it is a curve. Geodesic is a curve joining 2 points, for example say P1 and P2, such that the distance between the 2 points measured along it is the least. Okay, so this definition is rooted from the variational principle. Variational principle. That's why we take the distance to be the least. Now there is one more interesting property of geodesic, which says that geodesic is also a curve such that if you move along the curve from a point P to a neighboring point Q, then the tangent vector to the curve does not suffer any change. Okay, so you have a curve, you have a point P, have another neighboring point Q, and here you have a tangent vector, and here also you have a tangent vector. So the geodesic is a curve. Okay, geodesic is a curve such that if you move along the curve from a point P to a neighboring point Q, then the tangent vector to the curve do not suffer any change. So geodesic is actually a curve, okay, joining 2 points, and so such that the distance between them is the least, and also if you move from one point to the other point, then the tangent vector should not change. Then we have to derive the equation for such a geodesic, right? So next we shall derive the equation of the geodesic. the equation of geodesic. For that, we have to consider a curve which is parameterized by a parameter s. You have a curve x mu which is parameterized by parameter s. Then the tangent to the curve at a point P. So you have a point P. And the tangent to the curve at a point P, we have already derived. It is dx mu by ds. And I can also denote it by, for example, v mu. So this is the equation of tangent. So equation of tangent. Now I can travel a distance delta s along this curve and I reach a point Q. Okay, and this distance is delta s. Then if that is the case, then the total change suffered by a tangent vector. So the last class we have also seen that if you have a vector at one point, if you parallelly transport it to another point, then the components will not be equal. It will suffer a change. So the total change suffered by a tangent vector. Okay, total change. Total change suffered by the tangent vector from going from P to Q will be V mu plus del V mu minus V mu plus delta V mu. So this will be the total change. So this also we have seen in the last class. If that is the case, then limit delta s tending to 0, that is, I am going to take the derivative. Okay, so this is the difference. Here I can see V mu V mu and V mu will get cancelled. So remaining I have delta V mu minus del V mu minus delta V mu divided by delta S. Okay, this is the total change. But we know that geodesic is such a curve where the tangent vector will not suffer any change. Therefore, this change should be equal to 0. Okay, because tangent will not suffer any change. Okay, I can expand. So limit delta s tending to 0, del V mu by delta s minus limit delta s tending to 0, delta V mu by delta s is equal to 0. So the first term will be dV mu by ds minus limit delta is tending to 0. Now I have to substitute for the change delta V mu. Delta V mu is minus Christoffel symbol mu nu lambda V nu del x lambda divided by delta s. Now this is equal to 0. Now dV mu by ds, minus and minus will become plus. Now delta s tending to 0. So here I have this quantity. So plus mu nu lambda V nu as it is, and I have dx lambda by ds. So limit delta is tending to 0, del x lambda by del s is dx lambda by ds This is equal to 0. Okay. Now that we have seen the definition of tangent vector. So this is the definition of tangent vector. So v mu is equal to dx mu by ds. Similarly, v nu will be, if v mu is dx mu by ds, then v nu will be dx nu by ds, and v lambda will be dx lambda by ds. Okay, so these are all the definition of tangent. Definition of tangent. So here also you have dx lambda by ds, v nu. So these are all tangent. So I can write dv mu by ds plus Christoffel symbol mu nu lambda v nu v lambda equal to 0. Or I can write in another way also. So this is d by ds of v mu. V mu is dx mu by ds. Then mu nu lambda, v nu is dx nu by ds. V lambda is dx lambda by ds equal to 0. So here it will be second derivative of x mu plus mu nu lambda dx nu dx lambda is equal to 0. So this is known as the geodesic equation, or it gives the trajectory of a particle in curved spacetime. This is the geodesic equation. It gives the trajectory of a particle. Okay. Now if you carefully observe this equation, you have the second derivative d square x mu by ds square. So this is the forward acceleration of the particle. The forward acceleration of the particle. So if you want to determine the acceleration of the particle, then d square x mu by dx square, d square x mu by ds square is equal to, I can take to the other side, minus Christoffel symbol mu nu lambda dx nu by ds dx lambda by ds. Okay, so this is acceleration. This is the equation for finding the acceleration. Suppose you are considering a test particle, then the test particle will have a unit mass. Okay, so for unit mass, this quantity minus Christoffel symbol mu nu lambda dx nu by ds dx lambda by ds can be called as the force acting on the particle in the gravitational field. Force acting on the particle, because this is acceleration. You have acceleration here, and for unit mass, you know that F is equal to ma. So if it is unit mass, then acceleration is equal to the force itself. Therefore, for unit mass, a particle, a test particle with unit mass, this quantity is the force acting on the particle. Okay, acting on the particle, and from where it is coming? It is coming from the gravitational field. In the gravitational field. Therefore, if this is the force, so this entire quantity is now force, right? If this is the force, then the Christoffel symbol mu nu lambda can be considered as the intensity of the gravitational field, and hence it has the important role, right? So Christoffel symbol of mu nu lambda can be considered as the intensity of gravitational field. And we also know that this Christoffel symbol is a function of g mu nu. That is by definition. So if Christoffel symbol is the intensity of the gravitational field, then g mu nu must be the gravitational potential. Okay, so Christoffel symbol mu nu lambda can be considered as the intensity of gravitational field, and hence the tensor g mu nu will play the role of a potential of the gravitational field. Now, if g mu nu is the gravitational potential, then in the presence of gravity, the trajectory should deviate from a straight line. Because if you have a gravitational potential at some point, for example, you have the solar system and you have the sun here. Okay, so just imagine this is the sun. If this is sun, then due to the gravitational potential, the space around will be curved. Therefore, if a light is coming like this, it will not follow a straight line. It will always be a curved line, because the space around the gravitational potential will always be curved. Therefore, if g mu nu is the gravitational potential, then in the presence of gravity, the trajectory is given by the geodesic equation, right? If g mu nu is the gravitational potential, then in the presence of gravity, trajectory deviates from straight line. Okay, in the presence of gravity, the trajectory of a particle deviates from a straight line. So it's no more a straight line. Now, how do you show from this equation, geodesic equation? So at a glance, if you look at the geodesic equation, you will not get an idea. But the better way to visualize it is to consider the absence of gravity. Suppose gravity is absent. So instead of looking at the presence of gravity, we'll just look at the absence of gravity. In the absence of gravity, the gravitational potential will be 0. G mu nu will be 0. Then correspondingly, the Christoffel symbol should also be 0. So Christoffel symbol will go to 0 in the absence of gravity. Okay. If Christoffel symbol goes to 0, then you will get, in the absence of gravity, the Christoffel symbol will go to 0, which implies the geodesic equation will become d square x mu by ds square equal to 0. So this is the equation for a straight line. Equation for a straight line. So in the absence of gravity, the trajectory will be a straight line. So it says that in the presence of gravity, it is not a straight line. It will deviate from the straight nature. Okay. Now, the Christoffel symbol of second kind is the intensity of the gravitational field, and it is given by g sigma mu, then partial derivative of g mu with respect to x lambda plus partial derivative of lambda mu with respect to x nu minus partial derivative of g nu lambda with respect to x mu, right? Now, g mu nu is the gravitational potential. But here in this bracket we have gradient of potential. Gradient of potential. Okay, so that is why the Christoffel symbol is the gradient of potential, which is the field intensity. So this is gradient of gravitational potential. So this is gravitational field intensity. Now we can clearly see that the gravitational potential has many components. See g mu nu, lambda nu, nu lambda. Okay, so it's not a single potential. Gravitational potential has many components. Therefore, it will be a multi-potential theory. The Einstein's theory of gravity is a multi-potential theory. Okay, so Einstein's theory is also a relativistic theory. Okay, relativistic. Einstein's theory of gravity is a multi-potential theory. Now, under certain condition, we can reduce the Einstein theory of gravity to the Newton's single potential theory. So, Newton's theory is a single potential theory. It has only one single gravitational potential, and it is non-relativistic also. Under certain condition, it can be reduced to Newton's single potential theory, which is non-relativistic. Now, how do you do that? So, this can be done by a suitable choice of the coordinate system. So, one can always make all the components of the Christoffel symbol to go to 0 at any arbitrary point of space so that you can achieve d square x mu by ds square equal to 0. The choice of such a inertial system of reference means the elimination of gravitational field. Okay, so how do you do that? You have to eliminate the gravitational field by choosing a particular coordinate system. Now, if the gravity is absent, then you can say that the acceleration is 0. The acceleration is 0, or the velocity is a constant, right, or uniform velocity. So these are all the Newtonian single potential theory. Now, the algorithm that we follow to obtain the Christoffel symbol is something like this. First, you will have the equation for the metric. So, given a metric, you have to obtain the metric tensor, fundamental metric tensor from the metric. And once you get the fundamental metric tensor, then you have to find the Christoffel symbol mu nu lambda. So, this is the algorithm that we follow. Now, if we construct all the geodesic that can be possible from a world point P, then they can be classified into 3 categories. That is ds square greater than 0, ds square less than 0 and ds square equal to 0. So if ds square is greater than 0, then g mu nu dx mu dx nu. This is ds square. Okay, so this should be greater than 0. And such a space-time is known as space-like geodesic. Then if g mu nu dx mu dx nu is less than 0, it is time-like. Then g mu nu dx mu dx nu equal to 0 is light-like. Okay, so for the possible, these are the possible geodesic. 3 categories are possible. Now we'll see. Now consider a Minkowski metric. Consider a Minkowski metric. Then ds square is equal to eta mu dx mu dx nu. So this is the fundamental metric tensor in the Minkowski metric. So I can expand, I'll get minus c square dt square plus dx square. So this is the Minkowski metric. I can write ds is equal to, so this is ds square. ds is equal to root of minus c square dt square plus dx square. Now for light, if you are considering light, then the speed is equal to c. It's a constant. Okay, then ds by dt will be equal to, so ds I have to divide both sides by dt. Then I'll get root of minus c square plus dx by dt whole square. So in the case of light, we can see that any particle will have a velocity which can go maximum up to the speed of light. It can never be beyond c, right? So this dx by dt here can be either c or less than c. So dx by dt can less than or equal to c. It can never be greater than c. So ds by dt, if suppose it is c, okay, suppose if it is c, that is for the case of light. For the case of light, dx by dt is c. Then minus c square plus c square. So this will be equal to 0, which implies ds is equal to 0. So for light, ds is equal to 0, which is this case, the light-like. ds is equal to 0, which is also known as null geodesic. So light follows null geodesic. Okay, so light always follow a null geodesic. So this is if it is a light. If it's not a light, then ds by dt can take less than c. dx by dt will be less than or less than c. Therefore here it will be root of minus c square plus some quantity which is less than c. So some quantity which is less than c and its square, right? In that case, ds by dt will be less than 0, which is the time-like. So if it is light, then it will be ds is equal to 0. Otherwise, ds less than 0. Therefore, I can conclude that a real signal starting from a point P can proceed only in time-like direction or in the direction of a null geodesic. Only these two are possible. So a real signal starting from point P can proceed only in time-like direction or at the best in the direction of a null geodesic. Okay, because dx by dt can be less than or equal to c. It can never be, the velocity can never be greater than the speed of light. Therefore, we can conclude like this. Okay, so this is all about geodesics. So today we'll stop here.